So last time we have done the review of the differential equations, and we're going to apply that kind of mathematical tool to the undamped, free vibrations. And in chapter 2, we have two portions. One is called the undamped vibration. So that means a system vibration without damping. Okay, without damping, corresponding to is, in terms of our equation, ax double dot plus bx dot plus cx equal to 0. And that means this is the free vibrations. Okay, for undamped vibration, that means the damping term is 0. So that means b equal to 0 for undamped vibrations. Okay, so that means here we're going to deal with, in the two sections, is simply ax double dot plus cx equal to 0. That's it. So in this way, you can see in terms of the solving the differential equation mathematics, this system pretty easy to solve in terms of our exercise. Okay, and the contents of your homework 2 we uploaded, and deadline right now I'm setting is the end of the business day and the end of the day Monday next week. So the contents of the homework 2 basically is to exercise these undamped vibrations. Okay, so kind of give a head up. If you feel good, ready for the internal mathematics, I think you pretty much can cover most of the problems right now. Okay, so that is our contents for this. So we move on, and I will quickly go over this one. So the outlines for these undamped vibration systems will be, the first one is to, again, to review the exercise formulating the equation of motion. So that means that is most important. If the formulation of the equation of motion is not so accurate, so that means in this equation of motion, you're going to have such an equation formulated. If your formulation is not so precise, that means your coefficient A and C won't be so accurate. That means your answer won't be so correct. Even though you know how to solve for the equation, even though you know how to solve for the differential equation like this one, but if your formulation on A and C is not so is not accurate, then basically you got the wrong answers. Okay, so here we're going to do the exercise. Using this to formulate equation of motions, and here we're going to have a two method, and the majority, I think the first approach will be the most of the time be used, and that'll be good enough. And the second approach, using the conservation of the energy, and this method only valid for undamped vibration systems. For the second portion, for system vibration with damping, this method won't apply. So I wouldn't emphasize too much on this method. Okay. So again, our majority of the exercise will be on Newton's law. Before we're doing these things, and basically here showing you is if we will be able to solve for the system vibrations, and if we plot it, then the vibrations will be in the simple harmonic motion. For this one, you can see the amplitude pretty much constant. This is basically is undamped because of the internal vibration process. There's no damping. No damping, that means the energy won't be dissipated. So starting from the beginning, the whole energy, including kinetic energy and potential energy, pretty much conserved. So that means the amplitude keep constant. For damped vibration, this one you can see basically this decaying over time. So in terms of the magnitude, you can see this is an envelope in terms of the magnitude. Okay, if you remember from our exercise last time, again, if you remember, then you can see this is basically is e to the minus alpha times t. This is an envelope to kind of confine the magnitude. Again, if you have a lecture notes with you, turn a few pages before on Monday, we have been this one. Okay? And even furthermore, that is multiplied with magnitude x and cosine beta t minus phi. I think I use the kind of alpha beta notation. Basically, this envelope indicating is the alpha is the real part, right? Okay, so later on we're going to have more quantity relations involving the vibration notation. Okay, so for this case and for this case, they both are damped vibrations. And this one, you can see this one, the magnitude is kind of decay quicker. So indicating this system has more energy dissipated. So that means right away before really get the numbers down, you can see this one have a larger damping than this one. Okay, so that kind of quantitative, and before we really get into the numbers, and I think that's the kind of good feeling, you better to pick it up. Okay. And again, later on I will relate what is alpha and what is beta to the system's dynamics. That means to the damping ratio and natural frequency, etc. Okay, so that is our learning. But at this moment, we just have this concept bear in mind, then we can move on. Okay, so here we have this page. Basically, we have 3 categories of the vibrations. One is called the underdamped. This is the overdamped vibration. This is a quickly damped vibration, the underdamped vibrations. Okay, so we have such 3 categories, and corresponding to is this. And again, we think about the general, consider a general single degree freedom, free vibrations systems. Okay, so here to introduce these categories, and I will use the very general, that means K, C, M, and right now we simply consider the damping components for general descriptions. Okay, so for this case, and so if this is x of t, and that is our defined degree of freedom, okay? So x of t is a degree of freedom. So from this case, you can see if I have A and B displaced by that much, so basically from here to here, that is our displacement, and again, here I simply pick up my displacement along with the direction of the degree of freedom here. Okay, so that is the kind of assumed displacement. So on this one, basically we simply take the free body diagram on the displaced mass block. Due to such a displacement, the spring has been stretched, and again, right now I'm doing is a free body diagram, kind of general procedure to derive the equation of motions. Okay. So due to such a displacement here, basically in precisely this, such an assumed displacement is moving downward, okay? So due to this moving downward displacement, the spring has been stretched. So that stretched spring will will impose a force, and that put it upward to try to go back to the original configuration of the spring, okay? And again, due to such a displacement, because this is the dynamic system, so due to the velocity and in the same direction of the assumed configurations, that multiply with damping constant, and we will have the Cx dot, that is a viscous force being imposed by the damping component, and that is described by this. Okay, so that is a total force. And because this is a free vibrations, so there's no external loading applied. Okay, and right now this one using the Hooke's law, so this one should be equal to mx double dot. So that means in terms of Hooke's law, all the summations of the total force, the summation of all the forces will be equal to m times x double dot. And again, for this case, we assume the sign convection is downward. Okay, so that means the total force, according to the sign convection, basically is minus kx minus cx double dot, cx dot. Right, because here the two forces are pointing upward. Okay, so that one equal to mx double dot. So in this case, we rearrange mx double dot plus cx dot plus kx equal to 0. So this is called the equations of motion. Okay. So this is the equation of motion. Right now we can picking up our review of the differential equations from last time. So from last time, I using recall And last time I using is A1 X1 double dot and A2 X dot and plus A3 X equal to 0, right? So that is the notation. Right now we simply swap the coefficient in terms of the NCK. So in the similar process, so you can see the given the mx double dot plus cx dot plus kx equal to 0. So here this is characteristic equations will be equal to m. If we assume again here we simply plug in our notation we exercised last time from differential equation. We assume the x of t will be equal to say the a times e pt. Okay, we assume the sinusoidal oscillations. So that means mp squared plus cp plus k equal to 0. P is our characteristic root, charac root. P will be equal to, we have two roots, p1, p2. From here is 2m minus b minus c plus minus c squared minus 4mk, right? Be good? Okay, the same notation, the same template as we exercised last time. We simply replace A1, A2, A3 by N, C, and K here. Okay, so in the similar way, from last time, we have three scenarios, and basically depends on the value inside the square root here. So here I'm going to, using this notation to introduce certain terminologies. So again, from last time, we have the cases. That means if C minus 4mk is greater than 0, so that means from last time we have notation, that means the P1 and P2 are the real part, but they are different, right? So that is the real, but the different okay? So they are different real numbers. So for this case, this one, by combining into our terminologies in vibration, this one is called the overdamped. Okay, so here this is the new things I try to combine with from the between the mass and the physical system. The second one is C2 minus 4mk equal to 0. So that means P1 equal to P2 equal to the real numbers. We have two repeated real roots, characteristic roots. So for this one, in terms of vibrations, we define it's called the quickly, C-R-I-T-I-C-A-L-L-Y, quickly damped systems. Okay. And for the third case, if the numbers within the square root is negative, then basically we know that the P1 and P2 are complex conjugate. Alpha plus J beta, right? So here we have alpha beta appeared. So this case is what we know, these have oscillation with the decay. So this one is in terms of vibration we call it underdamped. Okay, so so here I kind of introduce the kind of map the definitions of the three cases to what we have learned from differential equations. So from last time we have done quite a bit of exercise using numbers to exercise solving the differential equations actually for the three cases. And I spent a little bit of time to discuss this case in the last three. And the case 3, again, if you remember, we have the system this time. For the case 3, last time I introduced is we have the envelope E minus alpha t here, and multiply with whatever the magnitude x. And the vibration is simply inside here, and from peak to peak or from valley to valley here, this is our period, and period t equal to 2 pi divided by oscillation frequencies. Our oscillation frequency is given by beta. This is what we have done last time, right? Okay, so here, if you forget the contents, turn over your slides or look up the videos, and we made on Monday about this detail. Okay, so from here you can see this is an oscillation curve like this, and that corresponding is for the third one, and that oscillation basically corresponding is this curve. You can see this is oscillating, and with the decaying magnitude like this. Okay, and compared to the first two cases, for the overdamped and quickly damped systems, and overdamped system is something like this. Okay, if we have a certain numeric values, if you can use MATLAB to draw the response, and that'll be showing like this. And this is a quickly damped system. Why we define this as a quickly damped system? Because the system is going to decay to zero at the, I would say, using using the least amount of the time compared to the overdamped system. Okay, so that is where it is defined like this. Okay, so with this one in mind, we can move on to the next slide here, and basically this one is to exercise our formulation of the equation of motions. And so for this case, with undamped system, basically here is again the procedure I kind of highlight here. So the steps is this. You simply define or pick 1 degree of freedom. Okay, for this one, again, this is only one mass block, that's a 1 degree of freedom. And for your exercise, you need to define your degree of freedom. Okay, and usually degree of freedom definition is pretty straightforward. For this case, we simply say you pick up this as your datum, okay, reference plane. And then you can define from here onward, that is the displacement. I simply measure the displacement of this reference plane, that is a reference plane to measure the displacement, and that defined as a degree of freedom here. Okay, you can define in that way, or if you like, you can define in this direction, either way. And once you define, you keep all your calculation consistent. Okay. So for this one, we pick up this one, we simply pick up like this. So once you have this one, then you simply draw the deformed configuration. So here I draw as a deformed configuration here. Okay, and that's a deformed, and you simply measure it and say from here to here, that is the displacement of this amount representing is the deformation of the spring, right? So from here, you draw the free body diagrams on the deformed block. So from here, on this side, attached is this spring. And because the spring has been stretched, and I say so because I follow up my selections here. Okay, so that is a kx. And this one must be equal to, again, because you pick up your degree of freedoms moving rightwards, so that means the momentum, the initial force must be moving rightward here. Okay, so under this situation, is mx double dot equal to minus kx. So that means mx double dot plus kx equal to 0. So that is the way to formulate the equation of motions. And let me demonstrate, compared to this one, let me demonstrate another way. Say, so again, this is the undeformed original systems. Okay, let me redraw it. So right now, say, let me exercise. If I want to, say again, I pick up this as a reference plane to measure. So here I define my degree of freedoms. Here exercise is moving rightwards. Say, for example, if you want to choose the leftward, so that is all degree of freedom like this. Okay, and let me exercise this scenario, and we see what happens. So for this case, simply we follow our selected degree of freedoms, and then we make a movement of this mass block. So along with the directions we pick, so that is the mass block moved to here. Okay, and from here you can see compared to the two distance here, this is the amount of the spring being deformed, being shortened. If the spring has been shortened by that much, so on this free body diagram, you can see the spring try to hover back. So that means the string try to stretch. So that means the spring exert a force on this deformed is that amount, but the direction is pushing, go that way, right? Okay. So now again, for this case, is equivalent to using Hooke's law, Newton's law, and again, this is the mx double dot. Right now, this is the initial force, and the initial force is to follow up our sign convention that should be moving in that direction. Okay, so here in terms of formulations, if let me say I pick the sign convention, like positive go that way, in this way the force will become as negative in terms of our sign convention here. Okay? So in this way, using this one, you can see mx double dot plus kx equal to 0, the same thing as we have this one here. So that is what I mean. If you select your degree of freedom and defining a direction, keep all the calculation, the formulation consistent with your choice, then eventually you should have the same expressions with everyone else. Good? Okay. In this slide, I want to explain for the first time officially why all the vibrations taking the degree of freedom. This degree of freedom is taken from equilibrium configurations. So for this slide, basically here I want to show you is this. Again, the keyword is all the vibration, all the degree of freedoms is taken or measured from the equilibrium configurations. Equilibrium configurations for such a horizontally figured example is really doesn't matter because the gravity won't take an influence. So basically, if the system is kind of the hand vertically, then the gravity will take into consideration. Then we do need to pay a little bit attention on what is the defined equilibrium configurations when gravity involved. And using this as one example here. So if this is spring constant K, and if this is going to hand a mass and that with a mass M, and if this is the direction of the gravity here, okay. So again, at this moment, the spring has been at this configuration is the spring is stretched. Okay, so right now here for this case, that means I put my hand at the bottom of the mass. I hold it such that I keep the spring unstretched. Okay. And that means right now I do kind of impose my kind of the energy to hold it. Okay, so right now the second configuration is this. If right now basically here is my hand. Okay, so kind of the hand. My hand hold it. Okay. So right now for the second scenario is this. I remove my hand, and also I have the mass being displaced to here. Okay. And how much displaced? Let me do the measurements, for example, from top to top. So basically from top to top, say, let me say that can be displaced by any number, let me call it y, okay? good. Can I? Okay. So for this case, the hand is removed. So for this case, this is the hand is moved but without any vibrations and still stationary. Okay, so that means I gradually move my hand away, and then everything kind of still in its stationary configurations. So under this case, this is in static equilibrium. Under static equilibrium, we can calculate the amount of this deformation. The amount of this deformation is such that the deformation in the spring, let me call it delta. And for the stationary, so the ST means the stationary. That means ST is these two words. Spring constant multiplied with deformation, and right now everything is in static equilibrium. That means equal to mg. And the deformation of the spring is going to hold off the weight of this mass block. And again, G is taken into account here. Okay, so that means delta ST is equal to, for example, here is mg. Divided by k. Okay. Okay. Under these situations, then I'm going to draw the third one. The third one, this is called the stationary. This is called our equilibrium configuration. So this one is called the equilibrium, EQUILIB configurations. Okay, so starting from the static the configurations again, and right now my mass block is moved to here. So we defined our degree of freedom is from where? It's from here. We defined our degree of freedom is from the configuration, from the equilibrium configuration. So that means starting from here. For example, for this case, this is our equilibrium configurations. We define our degree of freedom is xt here. Okay, so right now we're going to have a vibration start over. So this is a spring. So based upon this one, let me use the color. How about that? So let me use color. So right now I'm going to draw the free body diagram on this color here. So on this colored free body diagram of the mass. So you can see the whole mass is right now how much of the force exerted. On the top, that is the only the force will be only exerted from the deformation of the spring. Right now, how much the spring has been deformed. That is K multiplied with the deformation of the spring. How much? In addition to the static deformation, but also we have to add it on a little bit vibration. So that is K times ST, the delta ST plus X. And again, using Newton's law, this one is because we have a degree of freedom be assigned in this way, so that is mx double dot here. Right? Back to here, I kind of forgot one important term. For this term on this block here, in addition to the spring, but also due to gravity, we also have weight, right? The W. The W equal to how much? Equal to mg. So again, using the two equations and this kind of equilibrium, all the forces must be equal to mx double dot. So mx double dot right now for our calculation, we assume the downward is our positive sign. So from here you can see in this way that is minus k delta st plus x and plus w, right? And we can do a little bit of rearrangement, minus k delta st minus kx and w equal to mg equal to mx double dot, right? And from here you can see right away the two terms basically can be cancelled from each other because we have these relations. Okay, so that means this system becomes mx double dot equal to minus kx. That means mx double dot plus kx equal to 0. You see what this story tells? The story tells we reach the same equation of the motion like in this case, right? As long as you pick up your degree of freedoms from the equilibrium positions. If you pick out your degree of freedom, if you choose your degree of freedom definition from equilibrium configurations, then you simply can ignore the bothersome influence of the gravity. Because of your smart choice, the cancellation, the influence of the gravity basically will intrinsically cancellate during the process. So basically, we've done this one for a few minutes to now. Basically, is to tell you if you smartly select your degree of freedom from the equilibrium configurations, then in all of your the formulation, you don't need to consider the influence of the gravity. That's it. However, some people say, can I choose my degree of freedom from the unstressed configuration of the spring? Yes, you could. But in that case, you need to consider the influence of the gravity. So that means that is redundant because we know that that's going to cancel down the road. Why not you pick up the better options? Okay. So this is the official introductions why in our vibration statement we always pick up the degree of freedoms starting from the configuration, the equilibrium configurations. Okay. Equilibrium, that means the stationary, the everything is in static equilibrium. That's what I mean here. Good. Okay. So right now we have been exercised on the translation of degree of freedoms, and in a similar way we can apply to the rotational degree of freedom. So basically for this case you can visualize, basically this is the spring. So kind of spiral spring, okay? And this one kind of the hand on a disc. And say this one is the pivot point, say O. So say this one has a moment of inertia and IO, or sometimes people like to use JO, IO or JO, whatever the symbol, basically that's the moment of inertia, respect to the center over here. Okay. So from here we using again our degree of freedoms on stress configurations, and right now I say if we pick our degree of freedom, say counterclockwise or clockwise, either way, theta. Okay. So if we pick up the free body diagram here, let me draw it here. Okay. So because if we kind of rotating theta by that way, then the spring going to repel such change. So the force of the spring will be going in that direction. So that is the spring force here. And that is the deformation and spring constant K. Okay. And this one again will be equivalent to the initial force that is due to IO times theta double dot here. So sorry, the IO theta dot should be follow up this direction here. So again, using the moment about O equal to IO times theta double dot. So that means minus K theta will be IO theta double dot. In this way, IO theta double dot plus K theta equal to 0. Okay, So and the unit for this torsional spring constant is a little bit different from that unit in translational the deformation here. When we do the exercise, you will see the unit. So basically, again, for the spring constant, for the torsional spring, they have a little bit different units, but basically all the units should be consistent here. Okay. Any questions? Okay, we can do a little bit exercise here. So these are two examples. The first one is a pulley, and then here the example is to exercise how to formulate the equation of motion. So for the first one, assuming say the pulley, say okay, and this x is what we define the degree of freedoms of the vibrations we pick up, and say indicating we kind of choose is move downward. Okay, so here kind of they show you how to do the pulley, and probably you have learned that one very well in your statics, hopefully. But let me do this again. So say assuming this is a pulley. And we assume there's no mass here, and that means this pulley doesn't contribute anything to vibrations. So that means here is a single degree freedoms, and all the inertia is coming from this mass block. Okay, pulley has no mass, and this is a wire, and wire we assume is rigid. So that means this wire doesn't contribute anything to vibrations due to deformation of itself. No, we simply keep everything simple. That means that all the strain will be contributed by the spring only. Okay, under these situations, let me redraw the system again. So this is a pulley, and kind of the hold it by this one. This is a wire here. Let me just draw this one. And right now, I assume the pulley, due to the, say, right now, you can imagine if we kind of put the mass block downward, the pulley will be dragged down a little bit as well, right? So let me exaggerate. So say the pulley being deformed to such locations. Okay, so that means from here to here, this one, the distance here, representing is the deformation of the spring. Okay, and deformation of the spring basically is equal to this distance, right? So basically equal to this distance. That is the deformation of the spring. Okay, so right now I'm going to put a wire onto this drawing here. So the wire here, let me use blue line. Okay, so basically here is a wire. You see, due to the movement of the pulley downward by that amount, the wire going around will be changed double of that amount, right? So that means the wire originally deformed, say the point A is here. Okay, so for example, this is a point A, a certain point. I say I put a tape onto the wire at the beginning. And under these situations, where is the tape of A? So under that situation, so originally the tape of A is here, and due to this movement, the tape of A will be moving to here. Double of this amount, because the pulley going downward, not only this amount will be double together. So that is the location of the A, right? Need a little bit imaginations, or going back to your statics. And what is this one? Basically from here to here is what we defined our degree of freedom xt. You good? Okay, so in this way, put into this configuration, deformation of the spring is simply x over 2. Okay. Good. Seems not. Yeah, think about this one. So right now I draw the free bar diagram. I'm pulley. Pulley is rigid. And right now we have determined the spring formed by x over 2. That means the force applied to the pulley from the spring is k times x over 2. Okay. And the wire is rigid. And through the connection of the wire, you can see from here we have the mass, and which is mg. From here of the mass, and that is the, here is the tension, let me call it T. T is the tension in the wire. And this mass have the mx double dot of the inertial force. So basically from here, this is the tension of the wire, this is the tension of the wire. T equal to mx double dot. Here T equal to mx double dot. Because the strain is on this stretch, simply translating the force, and force is due to inertial movement, the movement, so that's mx double dot. So from here you can see again using this, and we have the total inertial force is 2mx double dot downward equal to the force and k times x over 2 put upward. So that means 2mx double dot plus kx over 2 equal to 0. That means mx double dot plus x k over 4x equal to 0. So this is our equation of motions.
So we're not feeling any inertia from the pulley.
Yeah, because pulley we assume no mass. No mass, that means no inertia. Yeah. If pulley have an inertia, that means we have to consider the moment of inertia. Then that will be additional term we added here. But here for simplicity, we don't. You good? Okay, so assuming this is good, then we can find the frequencies, try to solve for this equation here. So right now we have an equation x double dot plus k over 4m x equal to 0. So that is the equation from this case. I scale the first term to 1, so basically the equivalent to this. Okay. So assuming the x of t equal to a times ept, so therefore the characteristic equation is t squared plus k over 4m equal to 0. Okay, so p will be equal to I times minus plus okay. So that means this is the characteristic root. So plugging into our review of the differential equations last time, and that one basically is the A times E PT P1T plus A1 A2 E P2T. That is our formulation we did last time, right? So this one we can put into is A1. So E right now is I, let me define, okay, let me just do it. K over 4m T plus A2 E minus I K 4m T. We good? And what is this notation again? E alpha T equal to, by definition, is cosine alpha T beta T plus I sine beta T. Right? So using these notations, then Again, we can expand it. So basically, this one coming to here will be, again, do a little bit rearrangement. That will be C1 cosine K over 4m t plus C2 sine K over 4m t, right? So that is our formulation, the template for solutions. C1, C2 are determined by the initial conditions. On the other side, another possible solutions, another possible formulation could be, say, x times cosine K 4m t minus v. If you like, you can put into this expression as well. Either way, C1, C2, or capital X or phi, there's two unknowns. Two unknowns can be solved by two given conditions, which is the initial conditions here. If we are given the numbers, then we should be able to solve for this one. Okay, so from here you can see, basically either way, and you can see this representing is the frequency of the oscillations, or that's the frequency of the sinusoidal functions, right? So basically this is called the frequencies. And for this case, back to here, original here, because there's no damping, so we define the frequency here. K over 4m. Okay, so basically this one is called the undamped. This is undamped system. So we call this is called the undamped natural frequencies. Okay. So undamped natural frequencies, usually we are given a notation called the omega n. So which means this term equal to omega n squared. So usually for the expressions we have is this. The template is x double dot plus omega n squared x equal to 0. This is our standard template. Or otherwise we have an equivalent expression is this m x double dot plus kx equal to 0. That is a general, I would say, KEQ, okay, MEQ. We have a general expression like this. So that means compared to here, you can see, basically you can see that is x double dot KEQ divided by MEQ, x equal to 0. So who can tell me what is omega n? Omega n squared basically equal to this one. So therefore omega n equal to this one. KEQ, MEQ. Good. Okay? So n, that means the natural frequencies. That is the notation for this substrate n. That's simply natural frequencies. And for the natural frequency, there's two terms. And this is the first term I introduced to you. That's called the undamped natural frequencies here. Okay? And for the second question, for the second example here, basically that is the water in a pipe. And the mass of the water basically is proportional to the length of the water in the pipe, assuming the pipe have a uniform cross section here. Okay, so assume uniform. Okay, so therefore the mass of water is proportional okay, so let me assume the length is from here to here is L. Okay, so basically the mass, that means the mass equal to L. Not equal to, proportional to L. This is the proportional symbols here. And right now, we take the free body diagram on the deformed, assuming that someone kind of blow pressures from one end, so such that this kind of the water kind of they have a deform in this way, basically kind of raise up toward the right hand, the outlet here. And once that person's mouth is removed, then you can imagine this water going to back and forth, kind of the moving. Okay, assuming if there is no frictions, viscous force along the wall there, then you can see this basically will kind of be oscillating perpetually. Okay, so from this case, you can imagine. So this is the deformed. I take the free body diagram on the deformed configurations of the water in the pipe here. So again, this is our degree of freedom called the X. So the mass proportional to L times X double dot, that is the total inertial force going downward. And that won't going to confuse people here. So let me pick this one. It'll be easier to comprehend. So basically here, this is the degree of freedoms here. And let me pick up the degree of freedom in such a way to align with the change in the portions. So in this way, that is the X here. And on the other side, you can see the two portions. Here I highlighted is the change due to the pushing, the kind of change. And this one basically is has the length here is 2x. Right? And assuming the gravity is pointing downward, so basically due to this portion here, you can see the gravity, this one, the moment of inertia of the whole thing is moving upward, and then plus the gravity portion, and that is 2x. Again, this is a 2x of the mass, and multiply with g, that is due to the gravity influence due to this change portion, and this is downward here. Okay. So that basically is applying is the mx double dot equal to the force here. Okay. So now we, for example, if I pick up the say the sign convention, say the sign convention, let me say pick up this one upward positive. Let me rewrite this one is minus 2xg. Okay. So for this case, we have written is Lx double dot plus 2xg equal to 0. So that is our equation of motions. And again, let me put that one into our standard template like this form here. So from here you can see x double dot plus 2g over L times x equal to 0. So from here you can see the natural frequencies, the undamped natural frequencies will be equal to 2g divided by L. Okay, so again, from the very final step, I simply put into this kind of the standard template. That will easier allow us to pick up this kind of frequency here. Okay. And we can continue to take a look at another example here. That is the beam attached. So basically for this one, you can see this is the beam, and for this case, right now we assume the beam is undeformed, the rigid, that means no elasticity and no mass, that means we don't consider its contribution to the vibrations. And this is a pivot here, so basically the beam is free to kind of the tilting like this way. Okay, so the only mass is from here, from the end here. And for this case, for this example, first one we formulate the equation of motion, and then we find the natural frequencies. And again, here I will say is undamped, be more precise, undamped natural frequencies, which means we're going to find omega n. Okay. So for this case, we can take the free body diagrams. So this is the original configurations, and this is the deformed configurations. Okay, here I exaggerate, but here is our degree of freedom theta here. Okay, and due to such a configuration here, this is a spring, and the spring has been deformed, compressed. So that's going to have the spring force and point upward, try to going back to its original shape. So the force from the spring is K times deformed. And at this point, you can see if, say, let me pick up this X representing is the movement of the mass, that is our degree of freedom, so that means this distance is X. So in this way, the deformation here is X times proportional, that will be 8 over L, right? So this distance representing is proportional to this rigid triangle is that. So that means the spring force is A over L times X. Good? Okay. So under these situations, and also this is the spring force. And for this case, the initial force contributed by the movement of the mass is moving downward, mx double dot, right? Okay, so from here, if we take, because this everything is pivot on here, let me call the point O. If we take the moment, O will be equal to the you see right now I have drawn the initial term as the force. So in the general terms and the moment about the point O, including the true force and also initial force, must be equal to 0. Hopefully you understand my notation here. Okay. So assuming, say, let me pick up, say, a notation, follow up our sign convention, say this one positive. Okay, so under this case, for this one, due to the spring KALX, that is a spring force, and multiplied with this distance, how much is this distance? That one equal to A times L over X again, right? So this distance from here to here is A over LX. Okay, so this is minus because I pick up the sign conventions. And from here is mx double dot, that is the force multiplied with the arm times L. And positive because it's follow the sign convention here. So that is equal to 0. Is that right?
Why is your distance not A?
Yeah, I don't know.
Huh?
The distance from O
Oh,
should be A.
yeah. Sorry, my mistake. The distance here should be A. So this term should be A. Yeah, that's the reason kind of difficult. Yeah, thank you. Would say so. Thank you. Okay, so in this way we do arrangement. So that means M L x double dot is that right? I made a mistake. Okay. This one, again, then it's using the original notation will be better. So there's a pivot here. I think it's easier to make this. So under these situations, the total moment about point O will be equal to the initial force and multiply with L about point O there. Okay, so let me pick up these notations positive like this. So under these situations, I think the way should be like this. Again, I shouldn't. Let me stick back to the original Newton's law. All the initial force must be provided by whatever the moment. So we stick with this one. Okay. So under this situation, then we have plus k times a squared L x equal to 0. So that means here we rearrange and x double dot. Let me rewrite here. X double dot plus k over m times a squared L squared x equal to 0. Right? Okay, so for this case, you can see the omega n squared equal to this term. So omega n will be equal to k over m multiplied with a over L, like this, for this particular example here. Okay, so we can continue. So probably today we stop here. We can continue to